So in today's lecture, we will talk about inference about mu, the mean parameter of the normal distribution. Specifically, we'll talk about three things. One is square completion, technique of square completion, then posterior distribution, and predictive distribution. And if time permits, then we'll talk about inference of mu and sigma square together. So you have seen previously that the posterior distribution of mu pi mu given data was proportional to e to the power minus n over sigma square y bar minus mu square times the prior distribution of mu, which was mu minus mu 0 square over 2 sigma 0 square, okay, 2 sigma 0 square. And what is my target? My target is to write it write this expression as in this format: exp minus mu minus something square over 2 times something something something, right? This is my intention. Why? Because if I can write it in that form, then I can say that the posterior distribution of mu again follows a normal distribution with mean the 3 dots and variance with that multiple dots in the denominator of the exponent, right? So this is my target. And in order to write in that format, what I do, I combine the two square terms written in red color and do square completion. So I will explain this square completion not in terms of these notations, but in terms of general notations like mu minus a square b plus c mu minus d square in that form. Okay. So it is b mu square this technique called square completion. May I delete the lower part? This technique will be very useful for a lot of calculations, not only for this normal distribution for this particular example, but in future, you'll encounter other problems with a normal looking expression, and then you can apply this technique there to simplify the expression, to simplify your posterior density function. Therefore, this technique is really useful. Now, what I did, I have added some extra term that is free from mu, and I need to subtract that term. So the first term is b plus c, and it is mu minus ab plus cd over b plus c squared. Now, for our example, what was a and b? So for our problem, a was y bar and b was n over sigma squared, right? Am I correct? Without the 2 in the denominator, 2 must be there everywhere. So n over sigma squared. And c, what was c? C was 1 over sigma 0 square, and d was mu 0. Mu 0 was the prior mean of your parameter mu. Look at this expression. This term is the prior density of mu, and we assume that the prior density of mu is a normal distribution with mean mu sub 0 and variance sigma 0 square. So if I delete this part, let us delete this. So after our square completion, if I plug in A, B, C, and D in this expression, then we get n over sigma square plus 1 over sigma 0 square, then mu minus A times B in y bar over sigma 0 square, and C times D, which is mu, sorry. You see, here I have to be very careful about my attention. So mu 0 over sigma 0 square, and 1 B plus C. Now what is B? It is in the denominator, right? So it is n over sigma square plus 1 over sigma 0 square, inverse of it. And the other part is a square b plus cd square. A square B A square B plus C D square. I'm making mistake again. Okay, so this should not be sigma 0. And minus AB, which is n y bar over sigma square plus CD, which is mu 0 over sigma 0 square multiplied with n over sigma square and 1 over sigma 0 square inverse this part. So what we did, we obtained the posterior density function. Now, remember P mu given data is now proportional to, now this square completion was done taking the square terms in the exponent without the negative sign and without the 2 in front of both terms. So now I put a negative sign everywhere and put 2 in the denominator of this exponent. So it will be e to the power big square parenthesis and minus 1/2 n over sigma square 1 over sigma 0 square mu minus this entire thing, okay, entire thing. I call it dot 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 square times e to the power minus 1/2 n y bar square over sigma square plus mu 0 square over sigma 0 square plus 1/2 n y bar over sigma square mu 0 over sigma 0 square of it n over sigma square 1 over sigma 0 inverse. Now, when I consider the posterior distribution of mu, you see the second term. I have the two terms. One is the exponent with the orange color term, and the second term, exponent with some terms. The second term does not involve mu anymore. It is purely a constant term. No unknown parameters are there. No unknown parameter. So it is a proportionality constant. I simply ignore that part. Remember, in this setup, the first setup, where mu is unknown, but sigma square, population variance is known. Sigma square known, everything else is known. And the prior parameters, hyperparameters, they are called hyperparameters, such as sigma 0 square and mu sub 0. They are known, prior parameters. So this is a constant term. This is a constant and it does not contribute anything. Okay. No mu involved here. Data, is there, but data is given. It is treated as a constant in the Bayesian inference. So I ignore. So the posterior distribution mu given data follows a normal distribution with the mean and variance. Variance will be variance. What is the variance? You see, for a normal distribution, you have in the kernel part, you have mu minus something that is subtract from mu is the mean part. And the variance appears in the denominator of the exponent along with 2, right? So here, what is the variance term? The variance term is inverse of this guy. Inverse of this guy. So it is n over sigma square plus 1 over sigma naught square. Inverse, this is very important. What we make mistake. We forget to put the inverse sign. It is the inverse of that. And the mean is n over sigma square plus 1 over sigma naught square inverse and then n y bar over sigma square mu 0 over sigma 0 square. This is the posterior distribution of mu. Wonderful. Now, important thing is that the posterior distribution depends on the data. You see the mean depends on y bar. Y bar is the data part, right? It also depends on the prior parameters such as mu sub 0 and sigma 0 square. And the posterior mean is the weighted average of the data mean and the prior mean. Okay, prior mean was mu sub 0 and data average was y bar. You can see this is the weighted average. So this one, if I rewrite it as follows, y bar times n over sigma square plus 1 over sigma 0 square times mu 0. So I'm multiplying y bar with some weight, positive weight, n over sigma square, and mu sub 0 prior mean with 1 over sigma 0 square. And by dividing it by the total weight, n over sigma square, 1 over sigma 0 square. Right? This is how we do it. And so this is the weighted average. Prior mean, posterior mean is the weighted average of data mean and the prior mean. And the variance is also mixed. It is 1, look at this part. This is 1 over n sigma square plus 1 over sigma naught square. This is the variance. The variance is also modified with the variance of y bar and the variance prior variance. Now what happens if the sample size is, okay, so if let's do one thing. Let's divide the numerator and the denominator of the prior mean by n. Okay, n over sigma squared. Suppose I do that. So if I do divide it by n over sigma squared, it becomes y bar, and this becomes 1. Divided by n over sigma squared. So it will be sigma square over n. Right here, it is 1 plus sigma square over n. Right there. Okay, I'm just rewriting the posterior mean. What do you see? If n goes to infinity, then this term goes to 0, right? This term goes to 0, isn't it? If n is very large. So that means if you have a huge sample size, then what happens? Your posterior mean becomes your data mean. Posterior mean of mu becomes the data mean, data average, when you have huge sample size. In other words, if you have huge sample size, the effect of the prior distribution is reduced. So sample size, the effect of prior diminishes with the sample size. And that should be the case intuitively, right? If we do not have enough data, then we want the prior to speak. But if we have a huge data set in current data set, then we do not need prior distribution to speak unless we have a specific reason. And if we really want prior to speak irrespective of the sample size, then we can do what? We can reduce the prior variance also. We can reduce the prior variance. So what would happen? That means we have a very strong belief in the prior. That means we specify mu sub 0 and sigma 0 square is very, very tiny. So if sigma 0 square is very tiny, what happens? Look, in this expression, sigma 0 square in the denominator, right? So this entire ratio becomes very large. And it will be dominating then. It will be dominating. So usually, in many cases, not all the time, in many cases, we have some prior information, not very strong prior information, some prior information. So then that some prior information means a reasonable prior variance. The effect of the prior will be washed away as the sample size increases. But if we really have strong belief in the prior, then we can choose sigma squared to be very small, sigma squared 0 to be very small, so that it also has some dominating effect on the posterior distribution of mu. So yeah, so this is how we have written already. Do not make the connection with this symbol A and B, okay, with my expression of A and B that I derived on here. Okay, so here in this expression, I took A and B as some arbitrary constants, but now on the slide, I'm using A and B to denote this expression of the variance and the mean. Okay, as I said, if the sample size increases, then the posterior mean converges to y bar. And this guy, n times sigma n square. What is sigma n square? Sigma n square is this guy, sigma 0 to the power minus 2 plus n times sigma to the power minus 2 converges to sigma square, and consequently this happens square root of n mu minus y bar over sigma converges to normal 0, 1 in distribution. So the posterior distribution, center and scale posterior distribution of mu converges to standard normal distribution. This is the consequence if you have very large sample size. Very large sample size in this scenario, that your observations are coming from the normal distribution. Sigma square is known. All those things happen, then it happens. Now prediction of a future observation. Suppose that we want to predict a future observation, call it y tilde, from this normal mu sigma square distribution. Given the observed data, where each yi follows IID normal mu sigma square. So let us derive the predictive distribution. I can write y tilde, a new observation, as mu plus this error, where this error follows normal distribution with mean 0 and variance sigma square. So any normal random variable, I can write it as mu plus another normal distribution with mean 0 and the same variance. Okay, so this is just a simple linear transformation of a normal distribution. Now what happens? The posterior distribution of mu, given the data, follows this normal distribution. We derived it already. This normal with mean mu sub n. What was mu sub n? It is n y bar over sigma square plus mu 0 over sigma 0 square divided by n over sigma square plus 1 over sigma 0 square, that is mu n. And sigma n square is 1 over n over sigma square plus 1 over sigma 0 square. Now, if I use this distribution over here, what is the distribution of y tilde? Then y tilde distribution will again be a normal distribution with mean same as the mean of this distribution and the mean of this, and the variance will be added, this variance plus this variance. Now this is a consequence of this well-known result of the normal distribution. Let me first write this result. So suppose x, I'm just using x and y for two generic random variables, x, or I can use something else. So let's say u and v are two independent normal random variables with parameters mu1 sigma 1 square and mu2 sigma 2 square. Then u plus v follows again a normal distribution with mean mu1 plus mu2 and variance sigma 1 square plus sigma 2 square. Very important thing, two independent, u and v must be independent. Okay? Then this happens, and both are normal random variables, then it follows a normal. This is called the additivity property of the normal distribution. Some other distributions also follow additivity properties, such as Poisson, gamma, but not everyone, not everyone. So here we are applying this technique. The technique is very, very neat. We have a new observation, y tilde, and new observation is written as mu plus some noise. Now this mu under this Bayesian inference is parameter, but it's a random quantity, right? Mu is parameter, but it's a random quantity. So it has a distribution. What is that? Given the data, mu given data follows normal distribution with mean mu n and variance sigma n square. Okay, so this is one thing. Second thing is this guy. It is coming from the normal distribution mean zero variance sigma square. And why are these two independent? Why mu and epsilon tilde are independent? Epsilon tilde is the noise associated with a newly drawn observation. Okay, it has nothing to do with the error or the distribution of mu derived from the previous data. Distribution of mu given y is the posterior distribution of mu based on your observed data. So that noise has nothing to do with a future value that you draw from the population. Therefore, these two distributions are completely independent. Consequently, this total follows a normal distribution with mean mu n, and the mean of this epsilon tilde is 0. And variance is variance of mu, which is sigma n square, and the variance of epsilon tilde is sigma square. So now you can calculate those variances. So here I gave you another explanation of deriving this variance, but I think this intuition is a better explanation than calculating the variance in that way, iterative expectation. Okay, but definitely you can look at that explanation as well. Questions? So here is an example, ball bearing example. A process manufactures ball bearings. The diameters of 12 random ball bearings are these 2.487, blah, 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 all those numbers. Assume that the standard deviation of the process is 0.01 centimeter. Draw inferences about the mean diameter. So it's very standard problem. We can apply our inference technique here. Okay. This is my data set. And what is the classical estimate of the mean value? It will be the average value of those observations. Okay, and if I am interested, then I can calculate a 95% confidence interval of the mean based on the classical method. And the classical method is, this is the mean plus minus 1.96 times standard deviation of my data. Okay. Divided by square root of n, and this. What is n? N is the length. Okay, and instead of what about I call it y bar? Okay, y bar equal to mean of my data. Okay, and my SD is equal to SD of my data, right? Standard deviation, sample standard deviation. Because if I write this line of code, that means I'm calculating again and again the same quantity, but I calculated them once and then use them repeatedly. Y bar. Okay, so this is the classical thing. Okay? You can use any language. I have no problem. Okay, so this is the data. This is this. Okay, so this was your y bar classical estimate of the average value, and this is the 95% confidence interval using the classical method. Now let's do the Bayesian method. For the Bayesian method, we need to specify the prior parameters distribution, right? Prior distribution, prior mean, okay? Prior mean, mu 0, you can say 2.5, and the standard deviation, suppose I say 1, okay? Sigma 0 square 1. Sigma 0 square 1. So posterior standard deviation is square root of 1 over n over sigma square. Now sigma square is given actually. Sigma square is 0.01, isn't it? 0.01 or 0.1. Standard deviation is 0.01. Oh, I see. Standard deviation is 0.01. So sigma square is sigma square. Okay. So and since the standard deviation is given in the confidence interval calculation, I am supposed to use this standard deviation in the classical method as well. Okay, so it should be 0.01. 0.01. When the population parameter is known, it is better to use that population parameter. And posterior standard deviation is n over sigma square plus 1 over sigma 0 square. Sigma 0 square. Sigma 0 square is 1. So this is our assumption. Okay? And mu 0 is equal to 2.5. And posterior mean equal to n times y bar divided by sigma square plus mu 0 divided by sigma 0 square and here it is. Right? This is the posterior distribution. And so let's do that calculation once again. Posterior mean is this 2.4918. Posterior standard deviation 0.00288. Okay. And what was the classical estimate? Classical estimate was 2.491833. So it is the same, it is coming out. And the 95% confidence interval was 2.486175, 2.49749. Okay, so that is good. Maybe there will be some difference after few decimal places. Okay, unless we have done anything wrong in the algebra, but looks like this is correct. Okay, and mu 0 is 2.5. And in what was in is 12. Okay, next thing is a credible interval for mu. Credible interval, we can take 2.5 percentile point of the posterior distribution and the 97.5 percentile point of the posterior distribution. Okay, so I use this quantile, quantile. Quantile, actually we don't need the quantile because we'll be calculating theoretically. So Q norm that returns the quantile, and so it is 0.025 and 0.975, and the mean is this posterior mean and posterior standard deviation. So let us do that. So it came out to be 2.48617. Now let's look at what was this classical. The classical and the Bayesian are coming out to be identical because of, I believe, because of the very low standard deviation. Very low standard deviation. Now you may wonder why I took so low standard deviation. It's a the mechanical process. The standard deviation must be very low. Okay, keep in mind. Standard deviation must be very low. If there is a huge standard deviation in the process, that means it will not fit properly to all the ball bearings or whatever they produce. Okay. So standard deviation for a mechanical process must be very small. It is not like observational data from survey. Like if you collect data from survey on humans, then you have a lot of variability. But when it is collected on the mechanical system, you have very less variability. Questions? All right, so next we talk about, so another thing I want to talk about is the future observation. So what is the predictive distribution here? So this is the posterior distribution. Posterior distribution of the underlying mean. Posterior distribution, predictive distribution, sorry, predictive distribution of a future observation. So predictive mean will be same as the posterior mean, and predictive distribution standard deviation will be posterior standard deviation square of it plus the original data standard deviation square, variance square, which is 0.01 square, right? And then square root of this. I'm writing the standard deviation. So this one is the variance part, right? Sigma in square plus sigma square. This is the variance of the predictive distribution. I'm writing the standard deviation of the predictive distribution. Therefore, it is the square root of this quantity. And sigma square in our experiment is given. Sigma square is the population level variance, 0.01. Sigma is given as 0.01. So sigma square will be 0.001. And this is this. So I calculated predictive mean, predictive distributions mean, and predictive distribution standard deviation. Now, if I'm asked to obtain a prediction interval, okay, Bayesian prediction interval, what should I do? I'll use this distribution, calculate the quantiles from this distribution. So prediction interval. What is the interval that a future observation will lie within that interval with probability 0.95. So this is this interval. Quantile and 0.025, 0.975, PRED, PRED, and PRED, Let's do that. What happened?
Want to use Q.
Huh?
Q.
Oh, yeah, exactly. Sorry. You are absolutely right. I am supposed to use Q norm function, not the quantile. You use the quantile function if you have observed data and you want to calculate empirical quantile based on the observed data. But here I'm calculating the quantile based on the theoretical distribution. I gave the normal distribution with mean and variance. So this is the theoretical information. Absolutely. So this and so this is the prediction interval for future observation. Now you compare this interval with the credible interval for mu. Okay, you see this credible interval for mu was much narrower, right? The bottom one is the interval for the mean parameter mu, and the previous one is a future observation. Observation will be more varying. That is why you have much wider interval, right? A single observation is more varying, but mean parameter itself will be much less varying. Questions? All right, so let's end the class, and next day we'll talk about inference of two parameters.